All right. It's just going to have to be what it is. Yeah, sorry, folks. Bluetooth issues, hardware issues. Not coming back online. So I won't be able to... Oh, wait. Here we go. Just kicked in. There we go. Alright, never mind. We're good. Just don't touch anything now. Alright, welcome to the stream. Welcome back. I think we're going to work on Rosby tonight. I'm going to finish up what we did last week. I was just reading a little bit, some Reddit news and Hacker News. Databases. So this is like the announcement of Influx Data. They're going to be using Rust for their next generation stuff with Apache Arrow underneath. Pretty cool. I just thought it was kind of neat that there's some stuff here over operator control over memory usage. It's kind of important for Rosby as well. I think that's cool. This is a distributed database, so there's going to be a lot more stuff about replication and partitioning and that kind of stuff. So that's going to be fun to read about and learn about. Maybe we should do one in Haskell after we do one after we finish this one. Maybe we'll see. Yeah, some Haskell Reddit. I don't think there's been anything terribly interesting. Oh, the survey. Should probably do the survey. So I started a new job this week. It's pretty cool. I get to, luckily, fortunately, the grace of all the things that happened to bring me to this point, I get to program in Haskell full time. I'm working at a little company called Bank Mercury. I don't know, they might be hiring more Haskell programmers, maybe? But so far so good. Having a lot of fun so far. So now it's time to do some other fun Haskell hacking. And get to Rosby. So what do we got to do for Rosby this week? I think we had some undefineds that we need to figure out. So let's work on those. I feel like we're making pretty good progress on actually implementing insert this time. Only with zippers. Instead of continuation passing style. An interesting style to get to know, but kind of tricky. I haven't touched it a whole lot since I used to hack in Lisp, and it's pretty common there. But anyways, I'm having better luck with the zipper stuff, so. What do we got to do here? Let's review. Where were we? Unzipper, right? Move up, move down. Move to top. That's right. We had insert childs. Insert key. Okay, insert childs. That's the case where so we got KI. Oh, yeah, yeah. Okay, so we're going the B node light way. Yeah, that's right. And this is a little bit tricky to do. We can't just use an ordered map. That's right, because the number of keys we're allowed to have in the children are different. All right, so the challenge tonight is going to be the hard part of this, and getting a key inserted in the right place. In the split case where we had to split, like that whole merging operation we were going to do. That's right. And the other one is, what's the other case? That's where we have enough room to insert. Key value. So in the other case, we just have to recurse down to back down again, I think. Right, because we only insert keys at the nodes and we bubble up from the bottom. So the split is the moving up. Yes. Okay. Whew. It's going to be a challenge tonight. All right. So it looks like with insert key, is this the right type? We take a k and a vector of those k's. I guess we split it into two separate vectors. That's right. Not necessarily an A and a B, though. Is it? KI and K is plus plus. I wish I would remember what I was thinking about. This is cause for good naming. Oh, the key index that we're going to insert into. Yeah. That's keys. And we insert the child's based off the key index. Okay. Right. So insert key has to find out what index we're going to insert the key at, and I guess the vector of keys, the inserted key. We need the index because we need to tell child's, when we go to insert into the child's, which node to move down to and insert at. So that could be the one at the quote-unquote left of our index, and the one at the right of our index. To draw it out, just so you can see what I'm talking about. We have a vector of keys. Right, and by definition, we have potentially a bigger vector of childs, right? And this sort of this spot here goes to this child, and this index here goes to this child. 0th index and the first index. I'm putting it off of 1. Right. And the first element. 2, 3, right? So in here, there would be like your map with your key and value store. Right, this is just the node. And to do a less crummy drawing, kind of make it more obvious, maybe. Right, because it's an M-array tree, you could have. Actually, if I just separate them out, right, so key 1, key 2. Key 3, 8, 12, whatever. We branch. There's going to be a node between 2 and 3. Or let's make that 5. Right. And the numbers between, it's all, in the child knows, all the numbers between 2 and 5, including 2. So it could be 2, 3, and 4. And then all the numbers over here are anything less than 2. Say 0 and 1. Here. Right, it's between 5 and 8. Hopefully you get the idea, including 5s. Blah, 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 blah. That means we get 1, 2, 3, 4, possibly 5 child notes. And then we have 4 keys, and that would make this an order 5 tree. Right. So I wonder if there's a helper. I don't think there's going to be. I think we're going to have to write this one out for ourselves. But I'm kind of curious if there's a helper in vector for like this very thing. Or we kind of want to insert into the vector at a certain point and return the index. I don't think so. Pretty sure there isn't. What do I want to know first? Let's see. 9th? No. Modifying? Bulk updates? No. We don't want updates necessarily. Unless there's like a higher order update. Accumulations, permutations, indexing. Well, it wouldn't be very efficient, but we could. Using indexed would get us these pairs. And we need to search inside that vector for a value. Hopefully, if we sort on A. This should be ordered. If we assume it's ordered, then the one we're looking for, we would just write a search. Basically for the one that's just greater than the number we have, or the k that we have. And that would be the one we want to insert out. Greater than or equal to, because we have to handle 0 as well. So that's one approach. Not zipping. Not filtering. We could find the index, maybe. No, because we'd have to search pairwise. So that wouldn't quite work. Well, if we find the first one is strictly less than, 4. Actually, that might work. Yeah. The first element matching the predicate. Okay, and then in the nothing case, we take that to be the last element of the index. Whatever that happens to be, I guess we'll have to find that out. The size minus 1. Or the size, yeah, size minus 1. I think that should do it. We have some undefineds in here, but I know we won't be able to. So just try it out in our REPL just to. Oops. So let x's be beat up on lists. 2, 5, 8, and 12. All right. So it was find index. The function we have to give it is in some element a to bool. So it'll be less than what we're searching for. The element we want is strictly less than, so I'm going to use a little trick to flip that around. Hopefully this works. Let's say we want to insert 3 and 2 x's. And of course I missed a bracket. And what else? No, that should be fine. It's probably doing something weird with that operator. I'm trying to assert 3, 4. Nothing's less than 2, that's true. Well, that doesn't quite work, does it? No. Right, because it's going to find the first element, obviously, so. Silly me. Yeah, so we're going to have to go pairwise, because we have to find up to, like, the least most. Least most. Most least. Mostliest. Mostliest less than, but not too less than. The next, or we find the first one that's greater than or equal to us. That might work. This. Maybe that's the other way. We should do it the other way. Right, so we find the first one greater than or equal to us. That means the next index up. Up. That means, like, say, like in our case, and when in the REPL there, we were looking for inserting 3. We looked at this one first, then this one, and saw it was greater than or equal to 3. So we stopped here. This happens to be the index we would want for our function. No, we actually want 0. So we want the index just before that one. That's greater, the next one greater than us. I think that means the same thing. If we're trying to start 6, we should get 2 here, If we search 8, 9, 10, or 11, we should get 3. Or 12, anything higher than that. We should get 3. If we search between 5 and 8, we should get 1. Ooh, what happens if we do get 5? Yeah. Greater than or equal. Yeah, so that'll be 1. So it'd have to be greater than. I think is the gist of it. Alright, if we want 5, I want to get 2 from this expression. If I get 6, I want to get 3. I'm getting 2. It's not quite right. I don't think it expresses a relation quite the way we want it to. So you see, it's kind of... It's not going to find the between, so I think we do have to look up the pairwise thing. So that function is the indexes indexed. That's right. Well, okay. So now we got the tuples there. Yeah. So we need a function to transform, to go recurse through that list. Excuse me. Or maybe traverse it. Kind of pairwise, so it'd be nice if we can go through a pairwise, because then we can check right away. Was the element, the first element and the second element of the pair? Is our number between those two? Is there a way to turn that into pairs of pairs? Let's get to that. Well, vectors I might not want to do. Take the zip of the vector and the tail of the vector. Do we have a tail? I might do it. Head, last element. Well, we might have to just... could we do that? Partition, maybe. Scan. Well, what can that do for us here? Let's just accumulate the vector together. Well, take while. If we take while, all the elements less than this, then the length of that list, the size of that vector is going to be 1 greater than, or be exactly the index of the next element, unless the thing consumes the whole list. Then we're allocating an extra thing for Mary. I don't know. I'm only thinking of this in terms of, like, my brain's starting to go to the imperative place. Kind of ugly, hacky way we might be able to do it. We'll take b.indexed. To list. And if we want something that's like let's get it gross. Okay. Let's try it. See what we can do. keys. Keys prime. Let's make it. Well, we know we have to turn it to indexed. Convert it to a list. Make hacking on it easier. / more efficient. And then I need to return what if we don't find an index to insert into too, as well? That's going to be a problem. But we need to find the keys prime, and this key, plain old keys is what we're going to return. All right. Merge, right? Yeah. No, that actually needs to modify keys as well. Ugh, this is terrible. Yeah. What if... What if we partition? That might work. Maybe. Let's think about this for a second. If we partition the element by a predicate that is, say, the element is less than our number. We got our boxes of values here. 3, 4, 8, 12, 22. We want to insert 7 in sorted order, right, in the place where it's supposed to be. We also want to return the index that it was inserted at. Partition lets us define a predicate to partition a vector into 2. The first one contains those elements that satisfy the predicate, and the second one, those that don't. So if our predicate is less than 7, that means all the elements in the left will be less than 7, and everything in the right will be greater than or equal to. This will be 8, 12, 5, 8, 12, and 22. Don't change the overall size of anything yet. But if we were to sneakily recombobulate this, as we're going to, and put 7 here, right, that makes the index 0, 1, 2, should be 3, 4, 5, 6 and 7. Originally, these would be 3, 4, 5, 6. But this index here is going to be the size of this size of the partition. There are no elements greater or less than 7. And that'll be 0, and this will be 0. And we don't really care too much about anything over here. Because then we're going to presumably get an empty vector on the right-hand side if there are no elements there. And then when we join them back together, we should get the appropriate vector. So that might be the way to go about it. That feels pretty good. Okay. We'll just call them left and right. We got partition. Anything in our element array less than our key. So to put an OR constraint on K. And keys. And then we return a tuple that it was the size of the left and is a v dot length. Left joined with the v dot singleton of the key we want to insert, and right. Maybe a couple of problems there, of course. Good match, expected type A, electrical type int. That's okay, that's my problem. It's poor specification. It should be int. Vector K, yep. That's correct. Okay, cool. We got a hole somewhere. Yeah, I know, we got some. Let's look at these here. In this one, we couldn't match type maybe zipper KV with a zipper. Okay, I see. Yeah, we probably want to what are we going to do there? Yeah, I guess we probably want a pattern match on move up, because in the case of the root, when we have nothing, we can't move up anymore. No. Yeah, we just, when you get to the root, I don't think there's anything special you do there. You may end up having to split the root one more time. Or you might get, what else could happen? You could get a full tree. There is only a finite bound on the, depending on the order of the tree. So we can either, if we make merge up, return a maybe zipper. That's what I'm thinking. Or do we case split this and remove the maybe? And we either merge in the just case where we have a node, and if we're at the root, maybe it's a special function we need there. Or we just return the root tree as is. I don't think we do that. I think there is a kind of a special kind of merge. Or it's just a regular merge. By the way, I kind of just want to remove the zipper. So, maybe from this. We're going to do that here. So we just got to remove the maybe. And do it like that. I think in this hole, it's what to do with the value when you get it. Merge that with T. And if we get nothing, just T. This is the base one. Or not. Oh, right. Oh, that. I'm getting something mixed up here. That's what we started at. Second string. Okay, I think we're good. Yeah, okay. Sorry about that. Minor distraction. Okay, yeah, merge up was because we wanted to construct the node from the split, pass that in as an argument, and we wanted to merge that with the node above us in the zipper. So when we do the move up on the zipper, I want to merge with that currently focused node. Return that. Right. Okay. So this is just the zipper KV. So maybe we should pull the zipper. The reason I'm thinking is because we might want to merge. Only for at the root. That T. Oh, we only take a zipper, so it already handles it for us. Okay, so. In this case, with a whole zipper to zipper, yeah. And this is where should be able to partially apply merge with T as a function of zipper to zipper. For some reason this isn't. What am I doing here wrong, GHC? How should I like this? Can't even see the typers, all the other typers. It's not even that one. Got a red squiggly there, I'm not even sure it's actually a thing. It's 52, but I don't see 52 anywhere around here. Oh, maybe I mean editor's a bit messed up. Alright, okay, split. And that split is a product. Too few arguments, of course. I've only got a midpoint. I need to actually look up. I need to actually split something. That should be what? Work out the scope there. Insert with B-leaf. Right, so that should just be the V's, right? Figure it out for a second. Oh. Okay. Why does it think K is an int? Uh-oh. I mean, if it is, it is. It doesn't really matter. Oh. Okay. Like that. Let's... Oh, wait, it's probably that. Map module. Oh, that's right. Okay. So I should take the K first. Not K. Not KA, not KA. It's a tuple. Oh, but I guess since... Yeah. I think I see what the issue is. So mid is of type image, which is what's fixing it. Okay. Whereas we're kind of expecting a key, not necessarily an index. Okay. So we need to rethink this a little bit here. That is a bit of a problem. Okay, so we're in the first case, in the first guard we have mbet size is less than the order of our tree. That's looks fine to me. We just returned a bleaf with the inserted key value pair in it. And the breadcrumbs. That's it. Keep it. If we need to split though, we need to take a little element. Dang. That's probably why we needed to use vectors there. I was hoping we'd be able to use maps. Ordered maps. Unless there's a kind of... Unless there's a partition there as well. Because I think that's defined... I think that split function is defined in terms of relation on the ordering, so we might be able to change that away from like a specific index. So it's not an index. That's the key. Which means we can only talk about things in terms of orderings. Less than, greater than, that kind of stuff. Yeah. Partition. Partition with key. Partition. So this way we don't have to talk about key itself. We can just talk about it in terms of this function. So we don't have to set what. Oh, this is by value. Partition map according to a predicate. First map contains all the elements that satisfy the predicate. Yeah, so it's talking about those. We need to partition by key. So we have partition with key. Take while antitone. And then we have a responsibility here on ourselves for ensuring that all the keys J and K in the map. J is less than K implies that the predicate J is less than the predicate K. I think that will be true for us. Take while into tone. Okay. Well, that's take while. Yeah, okay. So mid, we just want to get the mid of the keys, the value of that key at mid, and then split on it. Split on that value. Oh boy. We have to make sure that K gets back in there. Subtle, subtle things. maybe we can do span editing. Divide a map at the point where a predicate on the keys stops holding. Let's give that a shot. So let's do 3A, say 5B, and I don't know, 12C. Okay, span anti-tone, where key is less than, so we're inserting 4. In ones. It's been edited. Sorry. I don't know why I typed B. That's good. 5. I think it's going to pose a problem. Nope. Okay, 6. So 3 and 5 should be on the first element of the tuple. It is. Okay. 12, and if we get 13, they should all be on the left side. Yeah, I'm going to do them on the right. Okay, let's fix that. Where key is... We still need to put... What do we need to put in there? Yeah, a KeyValue, not necessarily a number or an integer. So we need to actually look up the K at mid, if that's even possible. That should be K prime. Right? Yeah. Oh, except we're not dealing with maps here, we're doing a vector. Ugh. Yeah. So then, what the heck am I looking at? That parser. That's probably what's messing things up. Mm-hmm. That's supposed to be children. They get to be m.split. No, not these is supposed to be for me. So we're splitting those. It's supposed to be that, isn't it? Yeah, so calling them size on it. Right, we can't look up mid in these. That's completely wrong. What we need to look up is the array of keys, if there is, if we can get that out. So, just get the keys. Six to ascending list. Turn all the KeyValue pairs in the map. Ascending order. We don't really need to do that. We can just do the span into yeah. So let's just get rid of this while I do the mode. Like that. Elements less than. Okay. Trying to insert. And we have to wrap these back left and right back up into the leaves again. In the same order. Okay. I wonder if we added a, hopefully we added a smart constructor. We can clean this up in a second. I'm just gonna get it out here. Okay. Yeah, what's the problem with this line here? That's because so we have no instance or K from using insert key. Yeah, we need that OR instance. So the head, we don't know that the head of this vector of keys we've pulled out has an instance on it. And we just tell it up here. Apparently we can. In that case, we get the same thing here. Right, we didn't need to put 7 in. Okay. Or E. Okay. Yeah, it's just an interesting problem to have right there, or not that interesting, maybe. We define overflowed. It's probably a mistake if we're not using it. Right. Why don't we use it? So we don't need it. Right, we know we're in the overflowed case, so that's probably just a mistake. I don't really see a need for it. Pattern matches are not accessible in certain things. Take that. Okay, weird editor state. A real test. Does it build? I think it's just Haskell disagreeing with me. Or, not Haskell, Emacs. Because this... it's fine. There we go. Cleared that. Right up. Okay. See if we can clean up insert with a little bit here. Did we create a leaf? Mark constructor or like shorthand constructor, whatever you want to call it. Haven't. Okay. We could do something like this. Well, it is just kind of leaf. But we just want to wrap it with the... So let's do order, map, KV, to B tree, maybe. Not Mac. Map. Values. So let me just wrap this kind of up in a B. O and leaf of these. Now I'm going to shorten this up to olive left. And leaf olive right. Might even be able to do something with node in the same vein. Order these the vector of k, vector of b tree kv, b tree kv. We'll just wrap it back up in this order. Using child's keys and child's. Don't really think it needs to go point free there. It'd be a little bit fancy for no reason. So that means we can shorten this up to just node O. Okay. Could even move one, move two, move that from list, vector from list. Over here for the children. Can't really do it for K's, but no. We'll keep it uniform. It's okay if we go over the margins a little bit. Okay, cool, cool, cool. So what do we got now? We got insert with, splitting them leaves, merging them up to the nodes. I think we still need to handle the other case where we have insert with on nodes. Do we have any other undefines we should look at? Yeah, let's do those first. Hopefully they won't take quite as long. But you never know, you never know. So merging, we have a B node and where we're focused on another B node. We don't really merge in any other case. Oh, right, which is what we've already defined above. Right. Okay. So, in the otherwise case, though, where we know that the length of our children, so by merging these two children is going to cause problems. Because we won't be able to fit them. We'll have to split again, move up, that kind of thing. And we also have insert childs as well to this current range. gonna be tricky. This vector, what is this vector? The left. This one's a bit tricky too. I think when we insert child prime there, the second one, the vector of children, the children to insert into. We use siblings. No. We're merging into the focusing node. Merge a node with currently focused node of the zipper. Right. So the child's prime is the children to insert into. Child's are the ones that we're trying to merge. Now we know that ahead of time, through us being people and not computers, that child is only going to be a vector of length 2 when we're doing this merge. Haskell doesn't know that. And we want to insert the left children less than this. Right children around this. That's the appropriate markup. But the idea is that we want to insert those childs around that index. So this might not be quite the granularity of the function. Just quickly visualize it again. So for this case, where we're inserting childs, the child node that we're merging into looks exactly like this. It's got exactly one key, and it's children. Or like this. And since they're represented as a vector, of course, while they look conceptually like that, they look a little bit, it's a little bit more like this. Where we have a singleton vector of one element and a single vector of 2. Right, we have some other node that we're trying to merge into that might have 3 elements here, and a vector similarly of size, potentially size 4. And the otherwise case is kind of what we're, I think, what we're hitting, right? Yeah, if it's less than 2, then we have enough space. Otherwise, we don't. Or, sorry, we're not doing that right now. We're doing insert childs. All right, so we have enough space. We're in here. That means that we have enough space. This vector plus our 2 is going to be at least less than our less than or equal to our order. But what we need to do, if this key ends up being inserted, say, here after the merge, between these two, right? So let's make this one pink. If it ends up being like the one in between these two, then what we end up with is this. We have 2 on the end and 1 on the end here, and then we should end up with say this is an order 5 thing, then this should be up to 6. These are 4, so there should be 6. Right, so we want our children that we're merging down here to make sure that they're index-wise in the right place. So that they're there and there. And then the rest of the children are over here and over here. So that'll be like down there. Okay, so we have 5, sorry, 5, I didn't mean 6, 5. Right, for an order 5 tree. That's a bit dirty, a bit messy, but that's the general gist of it. Right. What could we run into here? Well, I noticed right off the bat, we actually do have 6 boxes. Probably where I'm getting confused at here. Right. We do merge that one in between. We can't have 6 children. So presumably, if this is 2, 5, 8, right, these are going to be less than 2. These are going to be 2, anything between 2 and 5. Going to be anything between 5 and 8. And this is going to be greater than 8. Presumably, if this is, say, 6, and we split a leaf node, these are going to be less than 6 and 6 or greater. So I just erased that whole thing. Can I undo that? Yeah. Everything greater than 6 on this side here. So if we insert that in there, that key, then we need to insert, would this be valid if we merged that one with that one? Not this one. No, that wouldn't make sense either. Am I even looking at the right structure? This would have to be in order. This would have to be in order 6. Yeah. Okay. So these two would still fit in this array here, or this vector. We just need to make sure that this box ends up on this side. This poses a problem, right, because these overlap. Yeah, so basically I think this one will end up merging with this one. We're gonna have to rebalance this somehow. That's tricky. What we want to end up with are 1, 2, 3, 4, maybe 5, maybe 5, 6. And this will still be 2, 5, 6, and 8. This would still be everything less than 2. This one would still be everything greater than 2 and less than 5. Or everything between 2 and 5, but less than 5. This wouldn't even be a valid tree. This would be a nonsensical tree. That's part of the problem. Let's make these a little bit longer. Say it's like seems like 38. This will be 5. 20. Oh, I'm getting all my stuff. Okay, let's slow down, back a little bit, and go back to the definition of the algorithm, the procedural one at least. Getting there, folks. Maybe the idea is that when we go split those children, we move up and we merge them. The idea of merging those children is to actually merge their maps together. Here's our handy dandy beach-route plus tree visualizer. Let's say we're working with a degree 5. All right, we start off with a leaf node of just 3. We insert 5. Right, that goes in and just finds the spot where it needs to be inserted. Slow down the animation speed a touch. Insert 8. Right, it finds that 8, it's going to go along, find that 8's greater than 5, and insert it at the end. Let's do like, I don't know, 15, 25, something like that. 14. Insert that. It's going to do the same thing. Gush. 23. Gush. And then split. Right. So we're at 4 keys. We try to insert 24. We get to 5 keys. Too many keys. Got to split. Gush. 8 became the middle one. If we were to overflow it and do it even slower, right, 24 goes in the end, becomes too many keys. 8 would become the middle-ish element. So then those become the left and the right. In this case, there's no other node to merge with, so that's fine. But let's just keep adding bigger numbers to it. That should go to this node here on the end. And if we get an even bigger number, it'll go to this node on the end and overflow again. Push, 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 split. And the middle one comes up here and merges. And we ended up here. Slow that down one more time. Gadoosh. Doosh, gadoosh. Doosh. Split and move up. Yeah. Right. So in our case, it's a slightly different. It's hard to see with this animation in our case and to visualize what's going on in Haskell. Because we're constructing a new tree off over here on the side that has 23 in it and 2 children. And supposedly those 2 children will be from here. Okay, so that intermediate step we saw before I started bringing the 23 up. Dink, drink, drink, here. Yeah. Right down there. To gank. Alright, that's what our zip operation is doing. We're moving up, but we're carrying this tree that we constructed with us. So that merge operation, if we step back, right, in our zipper, we're focused on this node down here. It's going to have, at the head of the zipper, this parent node, these 2 children. When we move up to do the merge, that's what we're focusing on. It's still going to have those 2 children on it. Well, we're going to have a vector with 2 new children in it. So I think that's kind of the same thing as just removing the last element, the last child, depending which side we're on, with the merging key. And removing that child that we just came from out of the list of children and just replacing our two vectors inside. Now it might be a little bit order dependent on where the key ends up getting merged into this parent node. So we step forward, Okay, we split there. Let's start inserting elements between 8 and 14 that will split this node here. And see what goes there. So let's insert 9. Goes here, goes down, bang, splits. Let's insert 10. Alright, bang, goes down, just inserts. We've got that part of the code working. Okay, and now insert 12. This is where we should call it as a split again. 10 becomes the middle one and gets inserted in the middle. So it does kind of matter where in this key vector it gets inserted. We just want to remove the old child from there and put our two new children in its place. Right. So what do we have in scope here? We've got the child, the thing we just constructed, and the parent node. Presume we have an equality instance on our B-tree node. No, that wouldn't work. So we get the index of where we get inserted in the keys. Wow, this must seem super basic, but maybe I'm just tired today. I've been working hard. Who knows? That was okay. And then child's could be up to 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Yeah. And if we end up inserting insert key function gives us 0. If the insert key ends up getting this function here, we get a key index of 0, or say 1, sorry. These, if they have values, we just inserted this, we're just merging this. Right, so it won't be a vector of this size. And our parent vector at this point, before the split, will be whatever order is -2, at least. So if this is an order 5, then child's will only be 3, size 3. And this... These keys... The K in that is going to be inserted in here. Does that, how does that mean? So this would be length 3. Initially. And this is child's prime. Would be this one here. So that's the parent node's current view when we move up from this zipper and do this merge. Just created this new index. And it's 1, which must mean that the value we want to replace is going to be 1. Is that what that means? Basically, if we're coming back up from a merge, we just move back up the tree, and we find that we can insert a key that the key that we're trying to insert. Or it may not be the key we're trying to insert. It's actually might be it's going to be like maybe some middle key from our leaf that we just split. Which means, what else does it mean? It means that the value itself, the K itself, is going to be less than this value, greater than this value. So if it has index 1, the prior tree guard might even be off. But the prior tree would be zero, index is 0, 1, 2. This could be 4. If we're coming down and splitting here, that means the newly created index right here is going to be between these two. Which will also be the same index. We went down to. If we went down to this one, and we came back up, then and split that one, that means the key has got to be less than this one, in which case our key index will be over here and 0. And so splitting that would work. And if we went on this side, came back up again, index, and split that one. And we would be basically putting a new index in here. Because this would have to be not set yet. But, if we smooth it too, yeah, okay. Yeah, so the key, that means then we just want to replace the child at that key index. I think there's a relation between there. I could be wrong, but I think that's the relation there. Yeah, we can split those up and insert them and merge them back together. And then I think we're going to be out of time for tonight, so I'm just going to try and whip that up quick. And so I'll get there. And so really what we want is children's insert. I mean, it's kind of hacky, but we're going to split that in two. Now our vector split function, as we recall, I think does include the element splitting on. Partition rule. Anyways, split. I guess that's the one. What else could we do? I guess we could do the index thing again. Take everything less than the index, or greater than the index. And recombobulate everything back together in a terrible, no good way. Or, what else? Right, because we have from list as well. Wow. Can we slice vectors? Yes. So we can slice a vector. split at. We do this. We could slice the vector, slice merged with the child's vector, merged with the other slice. Do this. Add index. C's and 2. Something like that. Beta slice from the beginning up to index combined with children that we want to insert, and beta slice of index plus 1 up until the end of season 2. Should speed of size. It's 1, I think. Season 2. Yeah, length. Oh, right. Let's give it the season 2 here. Season 2. Let's clean that up. Hopefully it doesn't, the slice doesn't include the index. Starting index with might be including the inclusive. But it might not be quite safe. I guess we'll have to test it out and stuff. This is pretty uggo. Where are we at now? Can we build? Still compile. Still compiles. We still have some undefines to clean up and finish. Boy. Okay, it was a bit slower night than I thought it would be. Oh well. But I think we're getting a bit of progress, and might need to clean some things up and merge some things together. Pardon the pun. Yeah. But hopefully that was fairly illustrative. And the next time we do this, we'll wrap this up. And we can move on to search and delete and update. Well, thank you for coming down and visiting, friend. May your monads always be free and your types always check. And I'll see you next week.